All right, everyone. So I think we can get started without like any further delays. So today, what I want to be talking about is JAX. So JAX is a new research language that was developed by a couple of people at Google. Specifically, I think most of the code was really developed by Matthew Johnson. It looks like in Hawken and P. As you know, there's a couple, and then this guy George Nicola as well is also at Google. This is Hawkins also at Google. Yeah, also at Google. Yeah, so it's a small team at Google that's developed this library, and I think that the goal of this library is to sort of be like a NumPy v2, like a NumPy made for machine learning. And so there's a couple of stuff they talk about here. So one, they say, well, we have AutoGrad and XLA brought together for high performance machine learning research, right? So what's AutoGrad? AutoGrad is the idea of you can basically get the derivative of an arbitrary piece of code. So a good example is here, for example. Let's just actually go through the Google Colab notebook because I think this will make it very obvious. All right, so I'm just call this like JAX test, for example. So yeah, so we have this. All right, so we're taking the derivative of the exponential of minus 2x, and then we're returning, like, so yeah, this is just like the 10h function, right? It's like another form for it if it doesn't exist. And then we're printing the gradient of this function, right? So let's say this was even simpler, right? Like, let's say instead we're defining something like square of x, right? And then this just returns x to the power 2. Right, so just like a very simple function. And then if you're taking the grad of square, this is the grad of square, right? So, let's say we print the grad square, what do we get? So yeah, we get the gradient. So basically it's an object which represents the gradient of a function. And if we want to apply it on some value, right? So let's say gradient of, let's say 5. So gradient of square 5. So it needs a floating value, that's fair. Yeah, so this returns 10, like y, right? Because the derivative of x squared is 2x. So x is 5, so 2x is 10. So that's pretty much it. Like, and the ideas here can be as complex as you want them to be. So let's say our function instead was define a square a conditional of x, for example. So the reason I want to say conditional is like I want to assume that there's some sort of if condition in the function. So let's say if x is greater than like 5, return x squared. Else, I want to return x. So this is sort of like what my this is like sort of a variation of a function that I want to have. Even maybe this could be 0. So this kind of has like a relu vibes, right? So okay, great. So let's say we want to take derivative of this thing, then we would say the grad of square conditional of x equals grad of square conditional, right? So we're just passing in the function as an object. So can't assign a local function call. Yeah, sorry, so I need to just remove this x. And now what we do is we just say, well, print grad of square conditional of, now let's take two different values. So let's say we take 6. Again, same issue with the floats, like let's 6.0. So we take 6.0, then it's x squared. And the derivative of x squared is again 2x, so 6 times 2 is 12. But now let's say instead we set 3.0. Wait, what's happened? Real. Yeah, so it's just like everything has to be floats. I think the issue is here then. So let's say instead if this returns 0, the derivative of 0 is 0, and so it returns 0. So this works even with code with like branch conditions. And so you can imagine like just like a more like case that you're probably more used to would be something like here. So let's say you're doing something that looks a bit like this, right? So let's copy paste this, and we can take a quick look at this code. So let's like look at the structure of this thing, right? So one, we have like basically, you notice like here instead of saying numpy, we're saying jax.numpy. So this is just like a way like to essentially make it easy to use numpy like features within JAX, like to use the same kind of syntax. Okay, great. So we know that the our function has some params. So we're gonna unpack these parameters. And then we're gonna say, okay, well, we wanna take the outputs where we take the dot product of input and W and add B, right? So this is just basically the WX plus B thing that you see in ML. And then you have here at the next step, like some sort of activation function. Oh, interesting. So here inputs is equal to, why is it returning outputs not, is this a typo? Yeah, I feel like this is a typo, right? Like this should be the opposite. Like the output is this, then you return the output. And then the input would be, I mean, okay, sure. Maybe they mean input to something else or something. Anyway, let's just not worry too much about this. So this like just like you can think of it as an like you're making some prediction, then you're making sure that the values go from like -1 to 1, I believe is the range of 10H. Range of 10H. Yeah, -1 to 1. Um, and after that, like, okay, well, here, like, you're making a prediction, for example. And so here, what they're doing is like log prod fun. They're saying, okay, well, we want to predict the param and the inputs, and then we will have our loss function be the squared loss. Okay. So basically, this is a prediction. This is how we get the loss for this function. And then we're gonna say we're gonna get the gradient of this loss function so that we can apply gradient descent on it and minimize it, right? Because and then JIT basically means that we wanna just in time compile this to the GPU or IPU. So this is sort of a way to get a high performance code in a dynamic language like Python. So you can sort of compile it line by line and then allocate those functions to the GPU or a TPU. So I'll talk in a second about how this works exactly. And then you'll see here what they're doing is they're saying, okay, well, we're going to also JIT this vmap function where we're basically doing something with the, we're getting gradients per the example. So this is basically, think of this as getting gradient of loss. I'll do it like this. So this is getting gradient of loss. This is applying uh, this is applying gradient descent, right? This is your loss function, and then this is your model making predictions, right? So, like, let's say you're using something like Torch, right? Like your predict would basically be your forward pass, right? So this is what your prediction is. So this is very similar here. So all right, so far like none of this looks really complicated. I guess like maybe let's like one thing we can talk a bit more about then is really like what's up with this JIT stuff, and then what does like VMAP actually mean? So let's like look at VMAP quickly. No, this is not it. Okay, I think it'll come up in a second. Let's just be patient. Right, okay, so far like this all looks fine. And let's just like look at like how they're sort of talking about this. They're saying, okay, well, you have these composable function transformations. Both grad and JIT are instances of such transformations. The others are VMAP for automatic vectorization and PMAP for single program, multiple data parallel programming of multiple accelerators. Let's talk about these each separately because I think these are all interesting. Let me bring out a tablet. All right. So one is we have, we already said we have the gradient. So you have gradient, which is basically, think of it like autograd. You have JIT, which is fast uh, iterative compilation for accelerators, right? So for by accelerators, this means GPU, TPU, IPU sort of thing. You have VMAP, which is automatic vectorization. So let's talk about automatic vectorization for a second, right? So when you're thinking about this, um, let's take an example, right? Let's say we have a vector A123. I mean, it's a list here, but let's just assume it's a vector. And then we have another vector, uh, you know, 3, 4, 6, right? So we have some sort of list that looks like this. So one sort of natural operation is a dot product, right? So how could you sort of do this, right? So you could say, for example, well, for AI and A, for BI and B, and then you could have like, let's say, some sort of result, right? And then you could say for AI and BI, then you could say something like result dot append AI times BI. Right, so this is sort of like a simple way to get a dot product. Wait a minute. Oh no, yeah. So this is like doing all possible combos, right? So instead, this needs to be for AI BI and zip of AB. Then we can delete this. Okay, right. So this is correct now. So the main point here is that basically a lot of for loops are essentially like vectorized computation, which hardware accelerators are specialized at making go fast. And so the interesting thing about this is like when you look at it, like your result at the second iteration here, right, is independent of what you got here and is independent of what you got here. So hypothetically, if this list was big enough, then you could have different subsets of A and B be handled by different machines. Or it can be handled by the same machine in multiple threads. So this is like the benefit of vectorization. It's sort of like this trivial parallelism scenario. And so then, like after that, they talk about single program multiple data. Single program multiple data. Think of this as like this is what GPUs do, right? So basically, the mul-add scenario. So you have two matrices that you're multiplying by each other. In this case, the basically the two vectors here can be independent. So assume this is vector A and this is vector B. Whereas here, it's like for every row in A, it's multiplied like you can do independent multiplications with columns of B. So this is why GPUs are good for deep learning, because GPUs are good for matrix multiplication, right? So let's just keep going. So here, over here. So okay, so they talk about having a couple of cookbooks, and then they're saying, okay, great. Well, our the main things we use is VMAP and PMAP. Okay, so you can take like multiple orders of derivatives, right? The derivative of the derivative. Uh, Reverse Morse Jacobian. Okay, sure. Compilation with JIT slow function. Oh, this is interesting. Let's try this out. Um, so let's go here and code. Okay, let's read this thing for a second. So what's going on here is that we have a function where we're multiplying x by itself, and then we're adding x and multiplying it by 2. right? So this benefits from Fusion, and I actually have a very old GitHub tutorial, GitHub compiler tricks. Uh, compiler, yeah, here, Fusion. So this is what loop fusion is, right? So remember, a lot of these compiler tricks are really just, you're trying to think of like what are patterns that show up in machine learning code a lot, and how can you make them faster? So this is one example. Let's say you have two separate loops, and you're basically looping over I, and then here you're looping over I again for some sort of other, and you're filling up values for two different matrices. Well, what a compiler is going to do is going to merge both of these loops, and it's going to make them do these operations at once. So it's sort of going to figure out what it can actually interleave. And the benefit of this is that, again, like this is easy to trivially parallelize, right? You could just say one core does I from 0 to 100, another one from 101 to 200, then 201 to 300, for example. So this could be like a very trivial way of splitting this problem up. In general, like here, when you're thinking about like vectorization, like here, like there's a whole Wikipedia page that talks about this. Like you can basically like infer some indices that you think will help you merge stuff. Maybe like if one of the loops goes from 0 to 300, another one goes from 0 to 400, well, you can merge them from 0 to 300 and then have the second loop keep going from 0 to 400. So there's also all sorts of tricks you can do here that generally a compiler does for you. But the interesting part here is that, like, okay, so we're just taking like an array that's all ones. That's I'm imagining as of size 5,000 by 5,000. We're compiling a function with the JIT, and then we're going to take the slow version and the fast version. Let's look at the difference. All right, so this took about 6 milliseconds, and this took about 100 milliseconds, right? So this is uh, like about like 50 times faster, right? Which makes a big difference. Like imagine you have a query that takes a day versus 50 days. Like so I want you to always be thinking about like when something is slow, that generally has a material impact to your productivity, because it means you can learn a lot more slowly. So just how to think about it. Like the syntax here is just saying like run this thing 10 times, run this function 10 times, run it on this input. So it's like a very useful decorator to use, like sorry, like a magic function to use in Jupyter notebooks that are very, very useful for benchmarks. Here, okay, let's look at automatic vectorization. So here, for example, we're saying input vec is on the right-hand side. Sure, where's input vec though? Oh, activation, yeah. Yeah, so one thing I really like here, let me just show you this for a second. Um, here. So typically, like in ML code, if you have something that works, like if you have code that works over examples, that code is not guaranteed to work over batches because you need to yourself come in and make the code work over batches of inputs. However, in this case, we wrote a function predict, which works over a single example. What we can then do is we could say, okay, well, we want to map this function that does prediction with these parameters to this whole set of input batches. And the idea here is that writing functional code lets you write shorter and more generalizable code. So this is something I'm extremely bullish on, and if you're interested, like tomorrow on Clubhouse, I'm going to be talking about this with a couple like really really smart experts that have very strong opinions about this stuff, and hopefully we'll learn more. So yeah, so this is how I should be thinking about this. Like a map is basically applying a function to every element of an input. So let's take an example. So let's say you have let's say okay, let's say you have a square function, right? Okay, so you have a square function, and now you want to apply this to every element of an array, of a list. So one way to do this is to just make a new square function that takes in lists, and another way to do it is to say, okay, well, I'm just gonna uh, say I want to map and then partial square on 1, 2, 3. So map, how do I make this return stuff? Oh, list, I see. Right? And this worked, right? So look, so this is 1, 2, 3, and we were able to square every individual element. So one thing I've been really wanting to talk about for a while now has been Haskell programming. So Haskell is something I got into a long time ago now, like maybe like 6 years now or something, but it's been really hard to find good use cases for it for my work. However, given that Haskell is like this purely functional language that's really great, it lets you build abstractions that sort of look like this. And so again, here, we did the square, but you could actually have something more useful where you're saying, well, actually, I want you to apply this model on batches of inputs, and then this will still run fast because you're gonna JIT this thing and still get like a decent performance. Right. So similarly here, like with VMAP, they're also doing something very similar. Like remember, so VMAP is a way to essentially allocate jobs to a GPU. And so here what they're going to do is, okay, well, we have predictions and we're going to map these predictions on these param with this like input batch. Or you could have like the slightly lower level. I'm not sure what like these n-axes mean exactly, but this is just like one way to think about it. And then when you're getting, for example, gradients, well, let's think about what that looks like, right? So you're getting a loss function and you have a gradient of a loss. That's a function, and you're getting the loss function is a function of two parameters. Like one, what your input was, right? Because your parameters are fixed. So once you know the input, you know what your prediction is, and then your target, because that's going to give you the loss. And so sorry when I said VMAP is made for GPUs. Like I apologize. Like VMAP is just for factorization. PMAP is what's made for GPUs. So let's take a quick look at what they do here. So what they're gonna do is they're saying, okay, well, we're gonna create like 8 random 5,000 by 6,000 matrices, like one per GPU. So what they're doing is they're gonna say, okay, well, we're gonna split what's random PRNG key. A pseudo random number generator key given an integer seeds. Okay, sure. It's just a way to generate like a bunch of random numbers. And then we're basically going to say, okay, well, we're going to create a matrix where we're mapping this random values over. Oh, interesting. Yeah, you see how this works? So let's say you have a function that for every element gives you, that you have a function that gives you random values. And you can apply this function on every element of a 5,000 by 6,000 matrix, and that way you can generate a random matrix. And then they're also saying, well, run a local matmul on each device in parallel, no data transfer. So here we're going to say a matmul. So we're going to take the dot product of x with x transpose. So that's basically just matrix algebra for x squared. And we're going to apply this over all of the values of the matrix. And so we basically have x squared being done on every element of a matrix. And so this gets back to, remember when we were talking about partials, like this is just a way of applying this and making sure that the partial application of a function is parallelizable and performant when it comes to GPUs. So the thing here is that like this is an example of a problem that's embarrassingly parallel, right? So here the like each value doesn't need, like each cell in the matrix doesn't need to communicate to other cells in the matrix to let it know what its value is. So what's lax? Lax piece. Let's look at what lax is. So lax, control flow, lax. Okay. Try broadcast shape. So that's just a way to like some convenience functions to multiply matrices. So you see also how like Python's gotten like nice and typed here. Like you can basically just have code that comes in, and you can say like, okay, this is an array. This is also an array. I'm assuming array is like defined here somewhere. All right. So here, but the point is like when you're doing something like a normalization, that essentially means that you're doing some aggregation over a bunch of elements of a list. And so here, like they're actually going to be communicating with each other. See here, yeah. So for example, here, and you could have like nested computation. So here, for example, we're saying we're going to take a sine, and then there's a function that we define which takes the cosine, multiplies it by the tan, does some sort of like aggregation, and then also takes the tan and does some sort of aggregation, right? So think of it this way: like if you're applying uh, g and p tan on x, then x is a if x is a vector, then this is going to be a vector. So then you take out the sum over all the elements of a vector. So what are some gotchas? So okay, so they can't deal that. So it only works with pure functions that don't have side effects. Uh, so what does this mean, right? Like this sounds very complicated, but think of it as like, well, if you're writing something to disk, let's say you're appending something to disk from a function, that has a side effect, right? Because if you rerun the same function multiple times, the state of your machine is going to change. But if you have like a square function, then it sort of doesn't matter how many times you run the function. Given the same inputs, you're going to get the exact same output. In-place mutation of arrays are not supported. I think this gets back to the purity point. Random numbers are different, but for good reasons. Let's take a look at this. If you're looking at convolution operations, they're in the JAX.lax package. So this is the sort of just like a subset of the library, which is for linear algebra. So JAX enforces single precision by default, and to enable 64 bits, you need to set the flag at an environment variable. I would imagine this is something they can just like fix over time. D-type promotions aren't preserved. Okay, sure. So basically, uh, numpy automatically casts data of various types. They have slightly different logic. So some transformations like the JIT constrain how you can use Python control flow, and you'll get loud errors if something doesn't work. Okay, sure. In terms of installing it, okay, so pip install, that's great. Uh, it needs like some sort of CUDA version, so this is always like a giant pain in the ass, which is why I'm probably just doing it for now. Oh, I'm just saying, I didn't know James Bradbury was the main person to was the first author, because it seemed to me like most of the code was written by yeah like George and yeah Peter and Matthew. I guess it's a big effort. In any case, I think like one thing that I always like to do when I see like a new project is I like to just like git clone it and then see about like how many lines of code this whole thing has. Just it gives me a good sense of the complexity of a project, even though like lines of code aren't nothing, but there's still a pretty useful metric. And so really the main thing that I thought was interesting is that there's a small minority of the code that's actually C++. That's interesting because like I'm suspecting this is like some CUDA level code. Uh, and if I were to imagine someone building a new and improved automatic differentiation library for linear algebra, I would have imagined most of this code would be in C++, but it looks like that's not the case. It's actually most of the code is in Python, like the vast majority of it, in fact. And so just like looking at the overall project structure, like we can sort of get a quick sense of what's going on, right? So they have like some sort of benchmarks here. And I guess like this is a good regression test, right? Where like if they make some changes and the thing breaks. Sorry, let me just get the light. Right, so they're making some changes. They want to still make sure that everything works fine. They have some way of building it to various devices, like with the build wheel, and sure, it all seems very nice and complicated. Something about like doing demos on TPUs. It's interesting, like the wave equation, for example. Let's take a quick look at this. All right, so spatial partitioning. Okay, that's cool. So you're partitioning a bunch of matrices. No, let's do something simpler, maybe. Okay, maybe yeah, the Lorentz ODE solver. Right. So okay, so here we're doing these ODE solves on a TPU. Uh, okay, we have some way of drawing stuff, but even like they're jitting the drawing function, so the even a drawing function can be ran. But I thought drawing would have side effects, right? Maybe it doesn't. All right, so true function, image adjust. Okay, this like I may need to just read this carefully. But yeah, like really, I think the function here, yeah, it's like these. So this is the differential equation or the Lorentz equations. So great. So we have these differential equations, and now what, right? So where are we using RK4? So we're using it in the solve here. Okay, that's great. Anywhere else we're using it? Okay, look. So essentially, we're basically p mapping various versions of the problem, and we're saying like like these can be parallelized and like run these on a GPU. So okay, so great. So these were p mapped, and then what are we doing with the ys, which is the answer, right? Parallel plotter, yeah. So I mean, like obviously this is complicated code, and if you're not like a, like the range CUDA integrator, let me just show you what it looks like, so you can believe me that this is, uh, you know, yeah. So this is sort of the differential equations for something like this, and that's what they basically did in the code. Like they just used this, but used code instead of using math. Otherwise, most of this seems to be occupied towards making the visualizations like nice and neat. Interesting. So there's some design notes about like let's say pseudo-random number generation and how this works in purity. This is interesting. What's omni staging? Infrastructure called omni staging improves memory performance, trace execution time, and simplifies JAX internals. All right. So this is just saying like, well, the project is still new and there's still lots of optimizations that they're doing to make sure that this works fine. Um, okay, so what's custom derivative? Differentiation rules, custom JAX, and to define custom differentiation rules for Python functions that are already JAX transformable. So what's an example? Because like I guess maybe functions that like really any numerical function shouldn't have this issue. So let's see, JAX custom transforms f of x is 2x. I guess like if you've solved the derivative of something analytically, then you could just like implement that in JAX directly without having to derive what the derivative is. So this is what I figured this is all about. Okay, this is great. So look at some docs, some examples, like the init, the yeah. So you see, like it's a bit of everything, right? Like they have like some Monte Carlo examples, some control flow examples. Here's an example with a data set. Right. So yeah, so it's the typical data download. Yeah. So just getting MNIST and then doing some permutation on it. This is like a permuted version of MNIST. Uh, differentially private confident. Oh, this is interesting. So the fact that it makes it easier to PMAP jobs onto several devices means that it should be relatively simple to do something like differential privacy, where you need to basically be adding Laplacian noise everywhere. Uh, so what's Stacks then? So Stacks looks like a Oh, it's like a neural net library, right? So this looks exactly like Keras, and you're saying, okay, well, I want to have a conv layer, a ReLU, max pool conv, ReLU, max pool, flatten, dense layer, ReLU, and dense, right? This is very typical to a lot of machine learning code. Your loss function is just your difference between uh, yourself and your logits, and then your accuracy, private gradient. So yeah, so the private gradient. So the difference here with the private gradient is that, let's see, so there should be somewhere Laplacian noise. Like here they're adding some random normal noise. Uh, Normalized noise aggregator, tree and flatten. Yeah, so essentially, like you can think of it as whenever you're making a gradient update, you would basically be adding some Laplacian noise to it, but it also looks like clipping the gradients first is one thing they do. So a clipped grade. Let's look at clipped grade pretty quickly. So evaluate the gradient for a single example and clip its gradient norm, right? So we're saying, yeah, so it's just like a way, like we don't want gradients to be too big. That's just like a way to make training more stable in general. And then the private version clips gradients. So that's really what it does first. Then it creates like some noise and then it adds the gradient and then it adds to it basically like the norm clip a noise multiplier for how much noise we should be adding. And then so where's private grade being used, for example? So private update. Yeah, so this is you see like the well getting a private gradient. Well, after that you need to actually update the weight. So you have like some weights, and then you just like Yeah, so here, this is where it is. Init param, iterate tools count, shape next image. Where is it? Oh, they're saying you can measure the privacy loss at any point in time, compute epsilon, and it's a function number example. So compute epsilon. So if number of examples is times target delta is greater than one, okay, great. Otherwise, you take the batch size and divide it by the number of examples. Orders, okay. So you set up this linear range, and then what's compute RDP? Oh, I didn't know TensorFlow had some privacy code in it. That's interesting. I guess that's like worth taking a look because this is a space where I haven't followed like the latest progress on libraries. Is there examples, tutorials? Yeah, it looks like regular MNIST, but you just add noise. Like there's nothing really fundamentally different about this example. Okay, so let's see what else is there. So we also have there's something. Okay, these are like the images, the logo images. There's JAX lib. So this looks like the CUDA stuff. So let's just take a quick look at this because I'm curious. Okay, so this is really about blast handle pool. Okay, like the different data types, the conversion. Oh, interesting. The conversions from JAX to numpy. Interesting. Okay, what's this? Unclear. Okay, so this is pseudo random number generation within CUDA. Q solver. Solve what? Yeah, actually, one thing I want to quickly talk about is XLA. Let me show you. So you can think of XLA as being like a compiler that takes your linear algebra code and then compiles it to run really fast without requiring too many code change. And it's sort of like I guess like the standard right now. Like it's sort of yeah. So here you see it looks very similar to what we saw JAX looks like, right? You can just say TF function with a JIT compile equals true, and that'll make sure that this runs fast. Gradient tape here is useful because it lets you explicitly get the gradient values and you can apply them yourself. So you see this, as opposed to if you're just using something like Keras, this aspect is hidden from you. Like you don't actually take the gradients and then apply them. But this gives you like flexibility for more just changing stuff more under the hood. Um, okay, so there's a bunch of stuff. Now let's see what actually JAX lib looks like. So there's interesting. So there's the ops, there's SciPy, there's some tools, the interpreter, something for images, something experimental. We'll take a look at this later. And then there's the source. So what's lax, for example? So lax seems to be here's like it's basically just keeping track of all the linear algebra stuff that we need to do. Okay, so what's lib? XLA bridge. Okay, great. I won't read this. I'm just assuming it's some way to hook up into. So this is the deep learning stuff. Where's the actual code though? Something with fast Fourier transforms and linear algebra. From JAX, that's source. Yeah, so it's all in source actually. Okay, yeah, so let's see. If we go to lax, init, nothing, control flow. Let's look at FFT, for example. Okay, yeah, so there's the FFT algorithm. There's the working with complex number versus real values. Okay, lax, I believe, was their linear algebra library. So yeah, so broadcasting shapes is just like very important so you can actually multiply things. Um, Basically, it resizes things to what it believes you actually mean. So this is more explicitly linear algebra stuff like Cholesky or eigenvalue decomposition. One thing like a very common pattern here is I see is the bind thing. Like, what does bind mean in Python? I think we'll get to it in a second. Let's see, and then some stuff for parallelization, like parallel traceables, compute an all reduced sum on X over the p mapped axis name. Like an axis, like let's say you have a tensor, like you're just picking like basically which column, not column, actually, like which, like let's say it's three-dimensional, like which of the three directions are you going to pick to do some form of aggregation? And then PMAP is just basically a way of, okay, well, how do you actually get this stuff to work fast on a GPU? You'll see that there's some neural network stuff, like they'll have like some simple activation functions, like, like, okay, like here's what ReLU looks like. It's just like it's like a max of the value and zero. So that's how you can make something, like, you just have like the derivative of a max function, right? So that's what the softmax really is as well. It's like a continuous version of the max function. The silu, which is just x times sigmoid x, log sigmoid, which is, so a lot of these loss functions you'll see like there's just like these one line code changes, and so that's why I haven't been particularly interested in papers that experiment too much with loss functions, because I just feel like, like there's not really much going on. So you just need to validate this in production to see if this actually matters. So there's an numpy stuff and some polynomial stuff here as well. So stuff like non-zero ranges. Okay, that's all cool. Some ops. Okay, so the scatter op is very important. So let me just show you. Yeah, okay, and SciPy, which is our optimization, sparsity. So how to multiply matrices where most of the values are zero by treating matrices like dictionaries instead of treating them like lists that you store in on disk or in memory. Okay, I'm not gonna go into all this like this SciPy stuff, but it's interesting that really it seems to be the scope is fairly big to me. It seems like, I mean, I call this a numpy killer, but it seems like the scope is much more ambitious for the project. So let me just show you the scatter operation very quickly. Scatter operation. So let's take a look at this. So think of it as you're doing some sort of like you're doing some sort of computation, and then you need to copy the result of this computation to x different locations. Whereas like whereas a gather operation is you're getting data from x different locations and then you're writing them all in the same place. So that's where the gather versus scatter nomenclature comes in. This operation shows up quite a bit in a lot of linear algebra algorithms, so that's why it's no surprise that it's there. So I think that's it. Like we sort of covered like we covered the code, we covered the docs, like sort of the main ideas in it. Certainly, I think like nothing beats just like messing around with it or having like actually one small project that we can dive deep into. But one thing I want to just finish up with is just like actually looking at their own custom docs. And so you'll see here, for example, they'll have examples for it works on regular numpy arrays, and that's probably because they have some nice conversion scripts that do this broadcasting operation. Jitting will generally make running times a lot faster, so that's just generally a very easy thing to do. You can take the gradient of any sort of numerical function. Maybe let me zoom in a bit more. You can take the gradient of numerical functions here, like let's say the sum of the logistic. It's all pretty fairly nice and easy to use. You can do automatic vectorization, which is basically applying some function on on the elements of a data structure. And so think of a matrix or a vector, right? All of these have different elements, so just applying the same function on every element is basically like a VMAP. So the benefit of this is that, like, let's say you're doing something like a prediction over a batch of inputs, then you just do a single code change, one line code change, and then you can make your same code work over batches of inputs. So what else can you do with JAX? So the key concepts, it provides a numpy interface. Through duck typing, JAX can be used as a drop-in replacement for numpy arrays. But unlike numpy arrays, JAX arrays are always immutable. So the mutability constraint is just generally important because it lets the compiler have stronger guarantees on how your code should behave, and so it lets it optimize stuff or remove it more. Um, let's see. So lax, for example, let's see. So like what do they say lax is? So you'll see that are eventually expressed in terms of functions defined in lax. It's a stricter but more powerful API for working with multi-dimensional arrays. Okay, so it's a multi-dimensional linear algebra library. So should you JIT or should you not JIT? That normalize the rows of a matrix. Okay, a just-in-time compiler can be created. Sure, sure. So here they're saying JIT. Okay, but here you get errors if you JIT. Why? Up by up mode. So get negatives. So basically, this is a filter operation. An array whose shape is not known at compile time. Oh, interesting. So the thing about jitting is that you need to have a guarantee on your input and output sizes. So this shows up a lot in deep learning with the ideas of a static graph versus a dynamic graph, where if your inputs or outputs are not of known shapes, it becomes much more difficult to do fast compilation. So the JIT here would just complain and fail. All right, that's great. What else can we do? The auto diff cookbook. Okay, so we already said you can take a gradient. You can take a gradient of a gradient. And this can let you do something like logistic regression, where you take a loss function and then get the gradients and then apply them. You can take the Hessian, which is like a gradient over multiple variables, and it's essentially what you're doing with in deep learning because you're taking the gradients with respect to a bunch of weights, right? So um, we're not going to go into the details of Jacobians right now, but what's also interesting is that this isn't constrained. Like like automatic differentiation works over any numbering system. Like it could work over complex numbers as well, which is interesting if you're doing stuff like Fourier with neural networks. Then this works nicely. Moving on, log densities. Uh, okay, I don't care about this. Let's keep going. The sharp bits. Interesting. I like this. I like this. Yeah, so they're saying there's certain constraints, like the functions need to be pure. So I talked about this already, as in, given the same inputs, the function needs to always have the same outputs. So writing to disk is really the main thing that involves things not being pure. You can't update things in place. That's also that's where the purity aspect comes in. Uh, oh, interesting. You may not get a failure if you index into the wrong thing. That's also interesting. Control flow. Sure, yeah. So you can also do this over control flow. Why will this fail? Okay, so this works. Okay, so we already tried something like this, right? And then here, then it trace your values encounter with concrete values concerned. Yeah, this is another interesting thing. So let's say the size of your input changes the like changes your shape. So let's say you're taking some example of like I don't know, you're doing graph neural networks, and if your network changes depending on the size of the graph that you're inputting, like the size of the molecule, it's much harder to compile. You have to basically compile a new graph each time. But if you pad it to the maximum size, then you can just compile it once and run that fast. But there's a trade-off here, right? Like it's simpler to not pad. Maybe the perf is even better, but padding means you can take advantage of more compiler stuff. So the more stuff doesn't change, typically the better compilers get. Okay, so here they talk about stuff like convolutions. Like, I don't think this is very important. Like they have stuff like padding, but you can imagine having this in any sort of deep learning library. In fact, convolution is just a generalization of matrix multiplication. So if you know how to do a linear algebra library, you'll know how to do a convolution library. We already talked about custom derivatives. Like I'm assuming this works really well. In the case where you already have an analytical solution for a derivative and you don't want to compute it, you just want to say like this is what this is, and then differentiate it. And this way you can intersperse code that's symbolically derived versus automatically derived. Um, So yeah, so the main JAX primitives are JIT, grad, vmap, and pmap. So here they talk about doing more stuff with it. So tracing here, this is basically a way to better understand, I guess, like the performance of how JAX works. So get like a lower level view of, okay, well, this is these are the functions that are being called, and when something fails, like, well, this is why it fails. So you can write your own interpreter. That's interesting. Your own tracer. Yeah, so you see this, like typically to figure out like how to differentiate the code, you would imagine that JAX would basically turn your like Python code into something that JAX can understand. As in, okay, like these are my inputs, these are my outputs, and then for each of these steps, this is how you derive it. And if you want to get more detail as to how this works, I'd really recommend you check out my tutorial, Automatic Differentiation from Scratch, because I explain how this works like in a lot of detail. So let's see what else is left. Oh yeah, okay, and we're at the changelog. So okay, no, frequently asked questions. So JIT changes behavior of my function. Okay, interesting. Yeah, I see. So this is like if it expects like multiple different kinds of inputs, like what you compile it to, it'll just work on that. It's very slow to compile. Uh, why would it be slow? Controlling data to computation device. Yeah, so like this is sort of similar to in PyTorch, you can just say to device. So this is, I guess, making it more explicit. Like this is the device I want you to send this data to. Different kinds of JAX values. Okay. Grade contains nans. This seems like a detail. We don't need to cover this. Yeah, so you can see here that like the core expression is sort of represented something like this. So this is looking like Haskell code, if I'm not mistaken. It's not Haskell, but it definitely looks like a functional language here. Ending PyTrees. But it's sort of no surprise because you can look at something called a data type in Haskell. So you see something like this, like Haskell, you can sort of define data structures like with like one line of code. So this makes your life very, very easy if you're doing this kind of stuff. So yeah, so moving on, you can, okay, call XLA to get the low level stuff that you need. Asynchronous dispatch, sure. How does profiling work? TensorBoard as a profiler? I wasn't aware. So this is very cool. I had no idea. Okay, how does the GPU allocate memory? What about concurrency? Sure, device memory profiling. pprof? What's pprof? Oh, this is very cool actually. So it looks like a Go library to profile stuff. These are very interesting actually. I may need to just look at this a bit more. PyTrees. Right, how is the JAX compiler? Yeah, PyTrees. So this is sort of like the data structure, I guess, intermediate data structure that lets you do the differentiation. Okay, rank promotion, sure. Type promotion semantics. Also, that's fine. What the updates? Yeah, so I think we're in good shape. So to sort of reiterate, what's interesting about JAX is it seems to be sort of like a reimagining of like what NumPy should be, where all code is like by default automatically differentiable, and where it's very easy to get fast and performant code that works well in both a vectorized way and can be run really fast on GPUs. And so, sort of, these are the main primitives. Otherwise, the code relatively looks very similar to what you would expect in NumPy. That said, once you have that core foundation of like the JAX NumPy version, it's very easy to build more advanced stuff. So, like a full linear algebra library with something like SciPy and linear algebra solvers, but also like a deep learning library that you can build on top to make this look like a Keras code. So as far as I know, like the fastest burst BERT implementations that Google have are right now still made in JAX. So that means this has become performant, but it also seems more expressive because it sort of embraces this idea of partial functional application and just this functional paradigm with pure and stateless code. It can make it very easy for you to sort of generalize your code across multiple devices, across batches, across models. And it's why I'm very bullish on functional programming in general for machine learning. And it's probably why I'll probably have a next tutorial be either on HaskTorch or on HaskTorch or on Dex, which is sort of a similar language. So yeah, so I mean, I hope you enjoyed this, everyone. Thank you so much for taking the time, and I'll see you all soon. Thank you.